Hello all, good day to everyone. I am N. Jashwant, a full-time PhD student working in Smart Transportation Research Group, Indian Institute of Information Technology, IIIT City. Today, I would be giving the part 2 of my tutorial talk on neighborhood discovery for autonomous driving in connected and non-connected vehicles. So, the outline of today's tutorial talk would be: initially, we get introduced to different sensing mechanisms for visual perception of complete traffic environment, like LIDAR and camera. Further, we would move towards understanding the importance of advanced technology and its integration for neighborhood discovery in smart transportation, like computer vision, artificial neural networks, convolution neural networks, and further 2D object detection models. And we would see some real-time applications which helps the driver in terms of assisting in the unconstrained traffic scenarios. First, so sensors for perception, LIDAR and camera. What is LIDAR? LIDAR is nothing but light detection and ranging. Basically, the LIDAR sensors offers a level of depth and dimension beyond the other sensors used in automotive space like LiDAR and camera. Mainly, it is used to find the precise distance of an object in relation to us. So, these sensors understand the world in 3D using the laser beams and measures the time it takes for the laser to come back. And it can detect the obstacles up to 300 meters and also can visualize in all directions. That is, it can provide the 360-degree, three-dimensional view of obstacles. As you can see in the figure, the arrow mark represents the Velodyne high definition LiDAR, which is commonly used in Waymo self-driving car. And the major working functionality of this Velodyne is such that the LiDAR unit emits the pulses of the laser light, then the laser beam hits back an object and pulses gets reflected back to the LiDAR unit. And then this LiDAR unit processor measures the time it takes for the pulse to return, which translates to a measurements of object's distance. However, there are few drawbacks when using the LiDAR sensing mechanism, as it requires the optical filters, especially for removing the sensitivity to ambient light, also to prevent the spoofing kind of attacks from the other LiDARs. And also, it is yet in research where they are exploring how this LiDAR, especially when they are using the laser pulses, is good and environmental friendly. But compared to the other sensing mechanisms like radar and camera, this LiDAR is highly expensive. So, what are the LiDAR principles? As you can see, the time of flight ranging. So initially the laser emits, as you can see in the figure 1, initially the laser in the LiDAR unit emits the short pulse of the light in the near infrared frequency band along some known ray direction. Once the object is detected, it scatters back the laser pulse in all the directions where some of the reflected light may travel along the original ray direction. And this entire thing is called as round trip time. So basically, to know the distance, that is r, you try to multiply the speed of light c by round trip time so that you can determine the total round trip time that is being calculated. As you can see, since the LiDAR travels much faster than the vehicles, light travels much faster than the vehicles, it is good approximation that all to think that LiDAR and target has been effectively stationary during few nanoseconds, all of these to happen. So that is, distance to LiDAR and target is nothing but half of the round trip time that's being calculated. This entire mechanism is called time of flight ranging. And as you can see in the second diagram, on the right hand side, it is nothing but the LiDAR unit is nothing but the LiDAR unit where it builds a rotating mirror in the LiDAR and that directs the emitting pulses along all the different directions. It means that as the mirror rotates in a particular direction, it measures the distance at points 2D slice around the sensor. So as you can see, the LiDAR functioning in 3D and 2D. Basically, the 3D LiDAR sensor report the range, azimuth angle, and the elevation angle along with the written intensities. It means that LiDAR measures the position of the points in three dimension using the spherical coordinates. The range or radial distance from the center of to the 3D point, whereas the elevation angle measured up from the sensor's XY plane, and the azimuth angle is being measured counterclockwise direction from the sensor's x-axis. You can clearly understand that azimuth and elevation angles tells us the direction of the laser pulse, and the range tells us how far in that particular direction the target point is being located. And as you can see in the top diagram, it is nothing but a point cloud. It means that the LiDAR unit tries to scan, and these particular points, the entire collection of points in this 3D scan can be simply seen as a point cloud. As you can see from the diagram, each and every circle representing in the first diagram is nothing but it is an individual scanned lines. So each point in a scan is covered by the intensity of the returning signal. So apart from the radar and lidar sensing mechanisms, there is a cost effective solution called as camera. So basically camera is one of the lightweight and also the low price point, and it is majorly used to capture the texture, color, and contrast information, which is helpful in terms of analyzing the object or localizing the object and the complete visual perception. So, however, even though it has the benefits, the few drawbacks such that this camera-based sensing mechanisms would not better perform, especially in terms of weather conditions like fog, snow, or rainy conditions, and also when there is huge variations in lightning conditions like reflector beams or even illumination conditions, etc. Apart from this, these camera-based sensing mechanism also do require extensive processing of image processing or even computer vision algorithms, and also huge amount of computing resources. So it also cannot see the beyond one layer of vehicles. It means that the line of sight could be only at the maximum of one vehicles and not beyond in front of that. So now getting into the deeper, the camera sensor models. Now given an image, we have to justify like few questions like how tall is this object, which object is closer to the camera focal length, and also what is the camera rotation angle and what is the focal length of the camera, etc. As you can see from the top figure, the tree is an object, and the light rays that is being projected on the particular object of interest is being captured and being projected onto a 2D film inside your camera, which you can clearly see in this particular figure. Initially, the rays on the object is being passed through an aperture and being projected on the 2D plane in an inverted manner. So during this process, it purely depends on how much amount of information in clear we would be gathering or capturing is purely depending on the aperture size of your particular camera. So regularly camera models are of two types like pinhole cameras and also lenses based cameras. So the drawback in pinhole traditional cameras is that the sharpening information is being missed, and also sometimes it may result in circle of confusion. As you can see, a few more properties of cameras like depth of the field, aperture, and also f number. You can see in the top figure that the initial aperture size is more. It means that the more the aperture, the less details are being captured, where the your sharpening information is being measured. So basically, the depth of field indicates the distance between the closest as well as the farthest object in the picture to appear sharply. And aperture defines like the amount of light rays being passed through the sensor. It means that smaller the aperture, the more depth of field. That means that the light where the depth of field is greatest, the larger the aperture, it means that the focal number is something like say for instance 2.8 or 1.4, etc. Then the less depth of field, more light rays is being passed, so that the shallow depth of field. So you can clearly see and understand that the lesser your aperture circle, the more you can actually capture the information of your object within the image. I mean to say the sharpening information. Next, so distortions. Basically, what is a distortion? Distortion is nothing but a kind of noise that being captured in the real three-dimensional world. So and these distortions, like tangential or radial distortions, typically cause because there is no proper alignment between the camera lens with the object in the three-dimensional world. As you can see, the object, that is the building, a vertical lines shown, and also these curvy surfaces like tangential and radial distortions. So this typically could be avoided by the concept called as calibration. What is calibration? So basically, camera calibration is nothing but it is the process of estimating the parameters of camera. Parameters include intrinsic as well as extrinsic. Intrinsic camera parameters include camera lens as well as focal length, optical centers, and also the radial distortion coefficient of the lens, etc. Whereas external properties or parameters of the camera includes like orientation, the rotation and translation properties of the camera with respect to the 3D world coordinate system is being examined. So once you are going to get the camera coefficient matrix after this calibration process, you simply apply this to the distorted image. So you can see from the figure, the original image shown in the left hand side is the distorted version of your image, where you calibrate your camera lens to get aligned with the three-dimensional world, so that you can exactly distort and avoid this kind of distortion, so that the image would look like as shown in the right hand side diagram. So now, apart from this, what are the some advanced technologies that really helps in the space of autonomous driving for neighborhood discovery? So let's slowly start with computer vision, understanding the fewer concepts of computer vision, which is a motive and also for especially for the visual perception of the complete environment. And then we would slowly move towards some concepts of artificial intelligence and also neural networks like artificial neural networks, convolution neural networks, and also two-dimensional object detection models. So as you can see, computer vision, so it typically differs from the human vision or human autonomy, eye autonomy. So you can see here this is a kind of anatomy diagram of a human eye, where typically we consist of cones and rods. Cones are nothing but representing your color representation. Especially they help us to visualize any object with different color in the daytime. We in a human eye has 6 to 7 millions in the retina. It means that we have that many number of cones, which is less sensitive to light. And whereas the rods typically help us to visualize an object better, especially in the night time, like gray level, etc. So you can see that rods has more in number when compared to the cones in the human eye anatomy. Next, and this is how the computer sees given an image. The left hand side is an image which is perceived by the human eye mechanism, whereas the right hand side is a kind of what is being seen by the computer itself. It means that it doesn't see the diagram as it is, but it tries to see an picture or the scene based on the raw pixel intensity values. Now the question is, can the computers match the human perception? It means that can the virtual or artificial computer vision can mimic exact human visual perception. Now, what are the different computer vision tasks that can be performed? Example includes semantic segmentation, where you try to take the picture pixel levels. So depending on the common pixels of that particular object, you try to categorize that this is a cat or this is like car or bicycle in the space of autonomous driving, etc. So classification and localization given the entire space. So for example, this is the entire image space, where this bounding box red in color representing only your object, that is it is trying to localize your object in the entire x and y two-dimensional image. Object detection is once again like detecting your objects based on some ground truth information like x, y, and width and height coordinates, etc. Next, instance segmentation. The only difference in semantic and instance is that in instance segmentation, you give a different color representation for each and every instance of a same category. Whereas in the semantic segmentation, irrespective of how many number of instances, you simply give a color representation for the particular category. So these are the typical computer vision tasks being used. But there are some real time challenges that we need to address. What are the real time challenges? As you can see from the first two figures where the object is being detected, which is representing or reflected in your image or mirror, but not in the real world three-dimensional world. So these kind of problems needs to be addressed, where it means that you can enlarge, I mean you can actually increase the amount of augmentation of your spatial samples, and make sure that during the training process all these kind of variants are being shown to your model for better training and understanding. Similar other challenges do include like viewpoint variation and illumination, scaling, intra-class variation, motion detection, background cluttering, and conclusion. Say, for instance, illumination, especially in the space of autonomous driving for night vision assistance, it is highly challenging to understand this scene in the night driving scenarios because of the high reflection of beams from the opposite end from the high HMV, that is high motor vehicles, etc. Next, other typical challenge in the space of autonomous driving include occlusion. Like, say, for instance, the heavy motor vehicles or the larger dimension of the vehicles would occlude the lane markings or other vehicles, so that which makes hard for the algorithm to perceive and detect the particular object or detect the lane for any kind of assistance like warning or even the lane deviation analysis, etc. Some of the recent applications in the space of computer vision include iris recognition, visual forensics, and facial recognition, etc. First one is an interesting case study where the initial picture of the girl, that is Afghan girl called Gulba, has been taken in the year 1980s, and then the similar picture has been captured by the same photographer in the year something around 2002. So then he has applied a iris biometric algorithm, which is used to superimposed graphics for automatic localization of iris and its boundaries based on some properties like, say, specular reflections and eye patterns, etc. So similarly, visual forensics for crime scene detection or anomaly detection, it can be used, and facial recognition was one of the good application in the space of computer vision, and also can be extended to autonomous driving for uh, driver assistance by in vehicle, like trying to analyze the cognitive behavior of the driver, like sleep patterns or drowsiness state, etc. Now, smart driving, as you can see, even in the tutorial talk 1, as you got introduced to radar and lidar and camera based sensing mechanisms here, there are few more applications in the space of smart driving, like lane detection, obstacle detection, pothole detection, traffic sign detection, and all these are being used for clear and adaptive nature of the visual perception of the environment, so that it can actually provide a complete, accurate, and reliable recommendation to the driver and assist him in any kind of situation or critical situations, or any kind of scenarios where it is the incident is about to happen. So now coming to the core concepts of artificial neural networks. So basically artificial neural networks is nothing but, it basically runs on two phases, that is where forward propagation and backward propagation. Now, given this particular diagram, this x1, x2, x3, and x4 so on till 1 are nothing but your input, that is your column vector, and then you have a synapse weights. Basically this neural networks has been taken, are being inspired by a kind of are being inspired by a kind of human neuron system. So this synapse weight would actually being, it's a kind of dot product between this, so that you fire this particular neuron, so through the help of activation functions, and being assigned to the hidden neuron in the next layer or set of hidden layers, that is used for classification and so on. So now this forward propagation is nothing but, from the input layer you keep feed forwarding, so that you end up with your prediction, that is the output, and you now compare the actual results that you have obtained with the target results. The difference whatever you are going to get is being further minimized by the help of concepts called as back propagation. So let's shortly see how each and everything are performed. So now the major components of any kind of artificial neural networks are nothing but input layer, next the hidden layers, then the output layer. So basically every layer, say for instance from here, after you dot product with the particular weights, you need to assign that particular values to the neuron. So this will be taken care by the activation function. The typical activation functions more popularly used are ReLU and sigmoid kind of activation functions. And this diagram shows the sizing of neural networks. It means that you can see the left hand side diagram. Initially, you have three neurons in the input layer, then the four neurons in the hidden layer one, and then two neurons in the hidden layer, output layer. Now, the number of neurons, that is excluding the inputs, are nothing but four. That is four neurons in hidden layer one, and two neurons in the output layer is nothing but six. So the number of learnable parameters would typically be 3 into 4. That is, you get totally 3 into 4, and it is once again connected with 4 into 2, so it is fully connected in nature. So you get totally 26, which includes even the bias. Basically, bias allows you to shift the activation function by adding the constant to the input. So now the question is, even though we have artificial networks, why we need to go for convolution neural networks, especially to handle imaginary data? Just imagine you have 1000 cross 1000 cross 1, that is one dimensional one channeled image or three channel image. Now just imagine how many number of, simply you get 3 million raw pixel intensity values, and you are taking one particular raw intensity values and trying to arrange in a kind of column vector. Now the issues are, it is computationally very expensive, because the more number of neurons would grow, the more number of parameters and connections would be established, and also the time is consumed is more. The second important challenge is that whenever you are going to take a row of intensity values and stretch it as a column vector, now the spatial relation between the first pixel and the, say for example, 1001 pixel in the second row would really be missing when you are going to arrange in this column vector manner. So to handle these particular things, you are having a concept called convolution neural networks. Basically, convolution neural networks have three components, that is convolution layer, pooling layer, and FC layer, where you finally apply some kind of softmax rules to get your classification or prediction. So this is the mathematical intuition. You can see it's clear that you have taken a 6 cross 6 image, and you are simply going to take a 3 cross 3 filter and convolve it based on the amount of stride, that is the moment you do, and finally you end up with 4 cross 4 dimension image. But the problem is, you may miss some amount of sharpening information in the outermost edges. To avoid this, you have a concept called padding. So you simply zero pad with the rows and columns, you add the zero padding, and you again convolve with 3 cross 3 filter, where you are going to not miss your exact spatial properties of your image. So it means that you are going to still have a 6 cross 6 image dimension. Then you, since you are adding a one padding, you get 8 cross 8 image. Then you do the entire convolution process, but still you are going to end up with 6 cross 6 instead of 4 cross 4 as your output dimensions of the image. So this is how it is being calculated: n minus f plus 2p by s plus 1. S indicates the stride, p indicates the padding, f indicates the filter, and n indicates your spatial value like height or row or column. So next, this is how the typical process would look like. Initially, you have the input image, then you do the sequence of process. You get, and you can see that each and every layer, how these features are being automatically extracted, and so that it can help us in localizing the object. Next, you have pooling and fully connected layer. So basically, pooling layer helps us to reduce the number of properties, especially it helps in spatial dimensionality reduction. And fully connected layer is nothing but whatever the convolution process you have learned the features that you are going to finally, now it's exactly the same as neural networks. You are going to completely make them fully connected in nature for further classification or prediction kind of analysis. So this is just a summary of your convolution neural networks. Now you can simply take a small three-layered convolution process, and you can understand going deeper how you got this particular 320. So 320 is very simple. So you have a 26 cross 26 cross 32. It means that you are applying the 32 filters of depth. It means that 32 is the depth of the filter, of which that 3 cross 3 is the filter size. So now you are going to add up the bias for each and everything. So you have totally 10 filters of such. So you are going to get 10 into 32 as a depth. So you get totally 320 parameters. Likewise, you are going to have the parameters defined for each and every trainable layer or learnable layer. So learnable layer is where you have some computation being performed. Say for instance, convolution layers can be called as learnable layers, whereas pooling layer you are simply trying to reduce the dimensions which could not be considered as a trainable layer. So and ending, you are going to have the fully connected layer for any further classification or prediction tasks. So some of the popular and well-known CNN inspired backbone architectures include VGG 16 and 19 models, LeanNet, InceptionNet, GoogleNet, and Alex and ResNet. And recent times, apart from this, the people are being even exploring the NAS related model, that is neural architecture set for lightweight, coming up with some kind of lightweight prototypes or solutions. And now the state of art is like efficient net is being used for classification tasks and so on. So this shows the clear cut example of what is the model and what is the size of the model and how much parameters does each model computes. So now coming to the object detection models. So with this inspiring motivation from the CNN and also the ANN concepts, the object detection models like RCNN, that is the region-based CNN, faster CNN, and also single phase of object detection models like YOLO and two-phase object detection models like fast RCNN do exist. This is an example of how we got the objects detected in the unconstrained traffic scenarios considering different and varied lightning conditions. So one of the popular well-known object detection models are nothing but fast CNN. So basically fast CNN is almost same as your previous version, that is nothing but fast CNN. The only difference is that there is an additional block called as regional proposal network. Basically this RPN is used to predict the region proposals, and further these region proposals are reshaped using the ROA pooling layer, which is then used to classify the image within the proposed region and predict the offset values for bounding box representation. So as you can see that even from the table, it is clearly shown that faster CNN consumes the less amount of time in trying to predict the particular localized object in the image, which is highly recommended for real-time usage. Next, there are few more parameters in the space of object detection like IOU, intersection over union, non-maximum suppression, etc. IOU will tell you that what is the intersection over union, kind to compare the predicted and the ground truth information. A non-maximum suppression is trying to avoid the other unwanted bounding boxes. Say for instance, in this diagram, there are bounding boxes with three different probabilities of the object being localized in that rectangle representation. So zero point 0.6 is probability, 0.9 and 0.7. Now you are going to set your threshold value where you are going to take only the higher probability so that you exclude the other bounding boxes. So the metric commonly used for object detection task is mean average precision. That is average precision. You try to take the average precision over each class and then try to apply the mean for that. Now there are some few real-time applications which typically includes like traffic density estimation and also driver drowsiness estimation. So driver drowsiness is simple. You are going to calculate the eye aspect ratio where you try to, it is simple. The numerator is going to compute the distance between the vertical eye landmark points. These are nothing but your landmark points, the green colored. And then the denominator is going to compute the distance between horizontal eye landmark points. And this is used for driver in vehicle analysis in case of drowsiness state and alarming or warning the driver so that before the collision occurs. Next, we have traffic density estimation, where we have worked as a collaboration with Tirupati Traffic Police, where we got the input from the surveillance cameras. We applied some image enhancement techniques like night vision enhancement, background subtraction, etc. So then you can see the results like the initial contours being detected and also the contour based tracking being applied, uh, so on. And few other results, as a part of smart transportation we do work on different aspects of autonomous driving like road navigable space recommendation, object detection, next pothole detection, etc. So you can see the bottom shows the GIF of recommending the free space in the road for the driver to have a clear visibility of the visual environment and also visual perception of the external environment. So the top figure shows it's an app where we have tested on in YouTube videos to see how this particular object detection being performed. So we have actually used the faster CNN to model this particular work, and also we have just transferred it into an app using the TensorFlow object detection API. Now, just finally to conclude, as you can see that the complete autonomous vehicles in India would typically take place in the 2050 or 2075. And also the integrated multi-sensor modeling, as you can see that each and every sensor has its own advantages and disadvantages. Nowadays, people are working towards integration of such sensor mechanisms like LIDAR and camera. There is one popular dataset called Kitty dataset which provides you both LiDAR measurements and also the camera based spatial inputs. So just to conclude, driving conditions, especially in developing countries like India, are highly unstructured and also unconditional in nature. So where we have a unique challenges that needs to be solved, and also there is good amount of research scope in the space of artificial intelligence, machine learning, and also there is good immense opportunity to have a good industry oriented collaborations. uh, Especially you can see like there are many good amount of labs like cognitive autonomous driving lab, cog drive lab, University of Waterloo, and Stanford, which has a navigation and autonomous vehicles lab, to get collaborated and work with them. So these are the acknowledgements. I would really thank all these contributors in the space of computer vision and deep learning for providing their material online, which helped me to understand the concepts and also for further assistance. I finally thank you all for your patience in listening. For any kind of queries, collaborations, and so on, you can contact the head of Smart Transportation Research Group, that is HV Raman at the rate of IIITS.in, or for any other assistance or kind of queries in the concepts, please contact jashwant.n at the rate of IIITS.in. Thank you very much.